Alright, so our first problem, we have a basic pulley. As you can see here, the diameter is 4 centimeters, and we've got a 20 Newton force pulling over here, and a 30 Newton force pulling over here on this side. So the first part of the problem says find the net torque about the axle on the pulley. So obviously we have a torque caused by this force and a torque caused by this force. We're going to do a little bit of setup here before we get too far. So the diameter is 4 centimeters, which we know that is 0.04 meters. Therefore the radius is 0.02 meters, which is half of that. So our torque formula that we know is torque equals the force that is applied times r times the sine of theta. So in this case, we're going to have a torque caused by this force and a torque over here caused by that force. In each of these cases, they are perpendicular. Both of those forces are perpendicular to the radius. Therefore, that angle theta is a 90-degree angle. So we'll call that one over there on the left torque 1, the one on the right torque 2. So torque 1 is 20 times 0.02, the radius, times the sine of 90 degrees, which is 1. So that turns out to be 0.4. Torque 2 is 30 times 0.02 times sine of 90, and that gives us a 0.6. Now, the thing that we need to note is that what we're calling torque 2 here is going clockwise, and that is negative rotation. What we're calling torque 1 over here is counterclockwise, and we've labeled that, and that is noted as positive rotation. So when we calculate the net torque, we're going to say 0.4 minus 0.6. Make sure I picked that minus right there, which is a negative 0.2 Newton meters. Newtons because this is the force, and meters from the radius there. So, part B. If the pulley has a mass of 5 kilograms, find the moment of inertia of the pulley. In other words, give us that number, the moment of inertia, which talks about how it resists rotating. So first we'll make a note here that the mass is 5 kilograms. We're looking for the moment of inertia. That's what we're trying to find. So we are going to treat this pulley and all future pulleys and problems as a cylinder or as a disc. So there's actually a set of formulas in the textbook that give the moment of inertia formula. It's actually really quite nice. You say, where in the world did they pull this from? Well, using advanced math, basically calculus, they can figure out, and mathematicians, physicists have figured out what is that moment of inertia for a disk and for all sorts of other shapes. And so that's the formula. And we use our textbook for that. And then plug in the numbers. 1/2 times 5 kilograms times 0.02 meters squared. And that gives us a value of 0.001, and the units are kilogram meters squared. That's the moment of inertia. It's actually pretty small for the situation. And so now there's answer A, answer B. And moving on to part C. Find the angular acceleration of the pulley, which is alpha. In other words, that's the rate of change in which it's spinning. So this thing is going to keep spinning faster and faster, or slower and slower. In this case, it's going to have acceleration. And the formula, Newton's second law of rotation, is that alpha is equal to the net torque divided by moment of inertia, which, conveniently enough, that was part A and part B. So we just plug in those numbers, and we end up with an angular acceleration of 200 kilogram meters per second squared times meters. Getting kind of cut off here at the edge, but if you remember, a Newton is a mass times acceleration, so it's a kilogram. The units are kilograms meters per second squared. We're multiplying that times meter, and we're dividing that by the moment of inertia. The units we saw there was kilograms meters squared. And so the kilograms will cancel, meter squared will cancel, and we just end up with a radians per second squared. Radians sort of a hidden unit in there. So It's negative because we've got the negative there, and of course that makes sense because this 30 Newton force is causing more of a torque, and so the object is going to rotate clockwise, which is the negative direction. Part D, if the pulley starts at rest, how long does it take to speed up to 100 RPM? So it's going to, how long, assuming that this acceleration was constant and this 30 Newton force was applied to it repeatedly. So we're going to say omega naught is 0 radians per second. Obviously, also, we're assuming there's no friction counteracting any of this. Our final angular velocity is 100 revolutions per minute, but we really don't like those units for angular velocity, so we're going to convert those into radians per second. So just turning that revolutions to radians, turning the minutes to seconds, we end up with a 10.47 radians per second. So now we have an alpha, an omega, and an omega naught. There is a formula that relates all of those with time, and that formula is omega equals omega naught plus alpha t. That's also on your AP formula chart. Solving for time, we get omega minus omega naught divided by alpha. Just notice subtracting omega naught from both sides, and then just dividing both sides by alpha. And then all we have to do is just plug in the numbers, 10.47 minus 0 over 200. That's going to give us a time of about 0.05 seconds. Sorry about that, it's hard to read that S right there. Last part, part E. What is the velocity of a point on the edge of the pulley when it is rotating, that's the whole object, at 100 RPMs? So at that final velocity. They want us to find, or angular velocity. So if you can imagine as this pulley is spinning round and round and round, and there's a point there on the end, then it has, we've talked about before, a velocity. We can talk about its velocity, and it's a tangent to the circle. It's linear velocity, so to speak. And that formula, as we discussed also earlier, is just r times omega, the angular velocity. So you just plug in the r, you plug in the omega, and you can find out how fast that particle will be moving. So 0.21 meters. So there you have it. A lot of this is really just plugging in numbers to the formula, but also knowing which formulas to use and how to interpret all these different quantities.